One of the most fascinating questions that faces geologists is how old is the Earth? There have been attempts made for centuries to work out the age of the Earth. One of the absolute first ones was done by Bishop Usher. What Bishop Usher did is he added up the ages of all of the people listed in the Bible and worked out that the Earth, since the Garden of Eden, was 6,000 years old. That was the first numerical estimate of the age of the Earth. Next in line comes Compte Buffon. Compte Buffon doesn't base his calculation on the Bible. Instead, he does it experimentally. He takes iron balls of different sizes and puts them in a fire, heating them up. The assumption he's working with is that the Earth is essentially a great big ball of iron. And it started glowing hot. So what he then does, he gets his assistants to take these balls out of the fire, lay them all up in a row, and they have to go forward and touch them to see how long it takes them to cool. And he measures how long it takes them to cool depending on their size. Of course, the small one cools faster than the large one. And then all he does is an upscaling to the size of the Earth, to the diameter of the Earth. And the number he gets is slightly over 70,000 years. I'm going to pop those down. I don't want to carry them with me. There we go. Lay them down there. One of the next players in this challenge of working out the age of the Earth was a Scottish geologist, also a farmer, a guy called James Hutton. James Hutton's working in Edinburgh during the Enlightenment. It's an exciting time. And James Hutton starts bothering himself with that same question: how old is the Earth? And to some extent, Hutton moves in the footsteps of Aristotle. Aristotle looked at the River Nile and how it meandered across the landscape. And he could see that there were remnants of the Nile having had different paths. And the whole idea that that mighty river could actually move its path and how long it would take brought Aristotle to the idea that the Earth had always been here. Hutton had that same kind of reasoning because, like Aristotle, Hutton looked at the landscape. I'm standing here now on a shoreline, looking out across the sea. It's beautiful. It's absolutely lovely. But at this very place, I can actually walk up to the rocks here and take a look at an ancient shoreline. And when I say ancient, it's actually 1.9 billion years old. So when we come up here to this lovely rock face, we can see that it's made of sedimentary layers, which are roughly parallel to my hand as I'm moving up the rock face. Each layer laid down one on top of the other, and they were actually laid down at an ancient shoreline on the edge of some supercontinent 1.9 billion years ago. How do I know they were at the shoreline? It's because I can see ripple marks. If I look carefully at the rock, I actually see that along that line, these are ripples. They were made by water flowing across that ancient beach. So here I am looking at the remnants of a beach from 1.9 billion years ago. And what's really, really special, if we take a closer look, we can see these little orange crystals. They tell us another story. And I want to head along the shoreline to a place where they're a little bit easier to see. So we'll wander over here a little bit carefully because it's slippery. Don't want to fall into the sea, that would be a shame. And we'll head up this slope up here. Perfect. Here we've got lots more of these beautiful crystals. We can see all these lovely rusty spots, absolutely stunning. We can actually also see places where they're not rusty. Here we can see them with they're actually a black shiny crystal. These are crystals of the mineral cordierite. Cordierite forms in the bowels of mountains. So what those cordierite crystals tell me as a geologist is there was a great big mountain range here if we go further back in time. Now with modern knowledge, I also know that that mountain range was actually 1.8 billion years ago. That puts it 100 million years after the beach we were looking at. But at Hutton's time, we didn't have that kind of age dating to work with. Instead, we can just marvel that we can be standing looking at rocks that were once a beach down by the shoreline, then a great mountain, and then there's been so much time that that mountain can erode away and wash into the sea. In the words of James Hutton, there was no vestige of a beginning and no prospect of an end. So old is planet Earth. So moving forward in time, another attempt to measure the numerical age of the Earth was done by Lord Kelvin. Lord Kelvin rationalised, somewhat in the same manner as Buffon, that the Earth was a glowing iron ball. And he studied how that glowing iron ball would cool by actually looking at how much hotter the Earth was deeper down. So what Kelvin did is he looked at the temperature and how it increased as we go deep down into mines. And what he finds out is that the further down we go, the hotter it becomes. And he uses this to calculate a cooling gradient. And then with the mathematics of the diffusion of heat, he's able to calculate how long it would take the outer part of the Earth to cool down. The number he ends up with is around about 100 million years, which with today's knowledge is a lot shorter than the actual age of the Earth. What was it that Kelvin had missed? Well, he missed that the Earth itself is able to heat itself up because of radioactive decay. So the discovery of radioactivity, which Kelvin didn't have when he was making his estimate of the age of the Earth, paved the way for us to be able to work out the age that we now understand that the Earth has of 4.6 billion years. I'm sitting in a pegmatite, a rock containing massive crystals. Now when this rock solidified, the radioactive elements that exist in small amounts, in, for example, these nice pink feldspar crystals, they start to decay. And that's effectively a clock. All we need to do is measure how much they have decayed. And then we can calculate an absolute age. The first person to do this was Arthur Holmes in the beginning of the 1900s. And he found that the rocks were in fact billions of years old. That set the stage for Claire Patterson in the early 50s, making the first estimate of the age of the Earth in billions of years. Claire Patterson found that the age of the Earth was 4.6 billion years. Thank you for listening.